For a recent project, I was struggling with the wire solver to build a network of interconnected wires that behaved physically correct. Full disclosure, I wouldn't have been able to get this working without the help of Esetela's CGWiki, which I'll link in the description, which is an awesome resource for Houdini stuff, and without Manu's help, who pointed me to using constraint networks for this type of setup. And what a constraint network is, it's just a set of tiny primitives that tells Houdini which wires connect to which wires. And to set up a constraint network properly, we need to know which format Houdini expects the constraint networks in. Let's assume we would like to connect those two wires here, wire 1 and wire 2. And these are the point numbers of the wire's points. So the wire solver expects, in our case, a polyline as a constraint. So just a line connecting 2 points. So what you would do is you would create a new line on those 2 points. Next, what we need to do is store the point numbers of the points that we would like to connect with the constraint. So in our case, that's 0.9 and 10. And we're going to store them as point attributes on the endpoints of the newly created polyline. Next, we need to store the type of constraint that we're creating. In our case, our constraint is called a wire glue, and our constraint type is a position, as it's going to constrain the position of the wires. And these are stored on our newly created polyline as primitive attributes. Finally, our constraint needs to store which wire object it's affecting. In our case, there is just one wire object, which we call wire, and this is the name we're storing in a point attribute again. Note that in our case, the constraints usually have a length of 0 because the wires directly overlap. They directly touch with the adjacent points. So what we're going to end up with is a polyline of 0 length, and on its endpoints we store the respective anchor points, in our case 9 and 10, and we store the name of the wire object to affect, in our case wire, and we also store the constraint name and constraint type as a primitive attribute of our newly created polyline. So let's build this. In Houdini, the first thing I'm going to do is drop down a geosub, dive in there, delete the file node, and drop down a sphere. I'm going to set it up to be a polygon, increase the frequency a bit, increase its overall scale to say 2.5, and increase its radius along one axis to make it elliptical. Then I'm going to drop down a mountain sub just to distort the sphere a bit, and just eyeball this in so I'll get a rough sphere. Something like this. Next, I'm gonna drop down a null object because then I'm gonna split my network flow. And in order to build my network of wires, I want to do two things. On the one hand, I want to build a volume with a VDB from polygons, and it should be a fog VDB with a filled interior and one band of exterior voxels, so that I just get a volumetric representation of my distorted sphere. And then I'm going to scatter points into this volume, like so. Let's say 100 points like this. On the other hand, I want to scatter points on the surface of that distorted sphere directly, so let's wire this up directly, like so. And let's decrease that count to, say, 30. Okay, the first thing I want to do is I want to merge those two differently scattered points. I'm going to do that with a merge sub, where I feed in both scatter nodes, so I have this resulting point cloud now. Okay, these are now all the points that I'd like to have wires in between, and I'm going to quickly create those with the connect adjacent pieces sub. Just wire that in here, and what the connect adjacent pieces sub does is, when I set it to adjacent points and increase the search radius, it's just going to connect closest neighbors. And let's decrease the maximum number of points to search so it does not get too dense. Like so. I have this network of lines now. Now when I display points, I see those lines only have 2 points and no intermediate points in between. I would like to change that by dropping down a resample node and maybe dialing up the segment length to, say, 0.2. So I have intermediate points along those lines now. Okay, but why did I build this with 2 point scatters, you may ask? Well, I need those 2 differently scattered point clouds to later tell my setup which points should be static, so which points should hold the whole wire network in place. And I'm going to do that by creating an attribute now. and wire this up to the points scattered on the surface only, because those are the points that I would like to hold the network in place later. So on those points I'm going to create an attribute called pin to animation. Like so, and I want this to be a point attribute of type float, and I want its default value to be 0 and its value to be 1 for those points scattered on the surface only. So now what I have to do is transfer the attribute from those points, so only those points that are scattered on the surface, to those points that make up my wire network. And I'm going to do that with an attrib transfer. Wire in my network here, and my static points in here, and set up my attrib transfer to only transfer point attributes and only transfer the attribute called pin to animation, like this. And in the conditions tab, let's leave everything as is except for the distance threshold, and let's dial that down really low, like this, so only really closely matching points get that attribute transferred from those points. Let's highlight this and dive into the geometry spreadsheet. And we see we now have points with a pin to animation attribute set to 1 and points with pin to animation set to 0. So now what did we do here? Well, on the one hand, we built this initial network of wires for our solver to solve. On the other hand, we told the network that there are certain points, which are those points here, which should not move. This is what we did with the pin to animation attribute that we created. So these points do not follow any physical behavior in the simulation, but stay in their place where we put them. And with the attribute transfer, we just transferred the attribute that we created on those individual points onto the points that are in our network that we created here. Okay, after we have that done, let's drop down a trail sub. And what the trail sub can also do, instead of just trailing geometry, is it can calculate a velocity, which we then can later use in our DOP network to drive a simulation or drive certain parameters of our simulation. And let's finally drop down a null here and call this out_wires. And this is our wire geometry that we will later solve in our wire solver. What we now need to do is create our constraint network. So the network that tells each of those individual wires which other wires they are attached to. And what a constraint network is it's just a set of really tiny wires that store primitive IDs of the primitives that should be connected together. So for example, in such a point here where all those individual wires meet, I would create another bunch of really tiny wires which just store individual connection IDs of those wires meeting here. So which basically would store those primitive IDs. And the quickest way I found to do this is like this. The first thing we need to do is create a bunch of attributes. And what we're going to need is 4 attributes. Like so. And we will start with the anchor ID. Let's set it up to be -1 by default, so it's not a valid ID. -1 as well. Now the next attribute we need is the original point number. And let's set that up to be -1 by default as well. Then we need the constraint name to store which kind of constraint we're creating, because there are different types of constraints. And this should be a primitive attribute, and it should be a string. Also, we need an attribute to store the constraint type. Primitive as well, string as well, and that should be all the attributes we need. Let me just check. We have our anchor ID, our original point number. We have the pin to animation attribute. We have our p-scale, which is fine. And on the primitives, we have the constraint name and constraint type. Okay, so we're all set up to create this constraint network. And you might wonder how we came up with those names for the attributes that we set here. So let's quickly dive into the help. And under the topic of constraint network node and the wire object node, when you scroll down, you will find a list of those attributes that both nodes take in to drive a simulation behavior. And all we're doing here is setting up these attributes and these attribute values for our constraint network to automatically build and evaluate those constraints that we are setting up. So after we created those attributes, let's group our existing geometry And let's set it up to be a primitive group, and let's call it wires, because those are just our standard wires that we just set up. Like this. Nothing changed until now. Now, the next thing we're going to do is actually create those primitives that store the connections of our wires. And the quickest and easiest way to do that is just with another connect adjacent pieces. And we're just going to set it up so it connects very close points together. So like all these points meeting here in such a corner, such an edge. When you see there are lots of point ideas overlapping, and we just want to create connections between those very close points here. So let's wire up the connect adjacent pieces, set it up to connect adjacent points only, dial down the search radius to something really tiny, and let's say max search points is, say, 15. Like so. So we only created very tiny lines in here where all those points meet. And the next thing we're going to do is create another point attribute, which just stores a name, and a name called wires. So let's do that with a point wrangle. And let's just type in there string called name equals wire. Like so. Now that I created those tiny connections in here, I want to only keep those and delete everything else. So those wires here, because I already created them here in the other geometry stream, I just don't need them. I only need the constraint network here. Let's delete everything else by dropping down a blast node. And let's delete the group we created before creating all those connections here called wires. Okay, let's blast that. Highlight it, and you see only those really tiny networks connecting the wires to each other remain in here. Okay, let's drop down another null. Call this one out underscore constraints, and we're good to go to set up our dynamic simulation. To do that, I'm gonna drop down a .NET here, wire in my geometry in here, and my constraints in the second port, and then dive in. The first thing I want to lay down in the .NET is a wire object, like this. And this is where I set up not only which geometry will be my wire, but also its physical properties. So how the wire will behave, how springy it'll be, how stiff it'll be, how much mass it'll have, etc., etc. But first, let's just tell it which geometry to use. And in order to do that, I find it very comfortable to use the operator syntax, the op syntax. So the way you use the op syntax is like this. Op, colon, and then it's a backtick. And on a German keyboard that is really hard to do. So I copied it. And then I'm going to drop down op input path. That's an expression which will yield me the path to the object that's wired into my first input. And again, close that with a backtick, and in here the op input path needs two arguments. One is the path where it should look for the object. That is just one level up. And then we can tell it which input slot it should regard, and that is the first one. So as we're in computer science, the first one is always the 0 input, like this. And we can see now we already imported our geometry into our DOP network. Also, what I want to do is set up the physical properties of my material here. So in the Material tab, under the Physical tab, I will disable Compute Mass and just give it a set mass of 1. Tell it width to be 0.01. That's fine. We can leave these as they are. And in the Elasticity tab, I will just increase the linear spring constant to be 10,000 instead of 1,000, and also increase the linear damping to 5,000 and the angular damping to 10, and I'm gonna disable the adjust for length and adjust for mass. I don't have a recipe for finding out these values. It's just what made sense and what looked good after dialing and fiddling around with those values. So these are the values that you're gonna experiment with. Also in the Plasticity tab, I just set all those values to be 0, like this. And in the Drag tab, I set the drag to be 0.15. Same for the tangent drag. This is just so that the whole wire construct dampens a bit, like it's got some wind resistance in it, some drag. Now let's wire this into a wire solver and set up the integrator to have a spatial scale of 20 and have a minimum subset number of 8. And let's dial down the solve tolerance to 0.05. 0, 1. Again, these are values that just made sense for my simulation, my setup here. Again, if you have a different geometry, different scale of geometry, you might want to change those parameters. Also in the accuracy tab, I just dialed down the maximum collision resolve steps to 1 because we're not dealing with collisions in this setup, so let's just dial it down really low. Now, the next thing I'd like to add is some gravity, like so. So the wires get pulled down, and we can leave that setup as is. Now, the interesting part is creating our constraint network. And that takes in our wires here. And it also needs a hard constraint relationship. And this will tell our constraint network which type the constraint should be. And in our case, it should be a wire glue, which will hold the wires together. Also, we need to set up our constraint network geometry that we created in the constraint network node. And again, I'm going to do that with the help of the op syntax. So it's op colon and then the backtick, op input path, backtick again, and it's going to point to a slot up 1 level, and it's going to point to the second slot that is counting from 0, first slot. And that should be it, fingers crossed. Let's highlight the output here, go up 1 level, oh maybe highlight the .NET here. Yeah, let's hit play and keep our fingers crossed. Almost, I would say. So let's see what's happening here. One thing that I totally missed was that I modified the connect adjacent pieces sub here. So let's right click on it, say allow editing of contents, and dive in there. And this might seem confusing, but the important thing is in this node here. And this is the node that creates those connections from the nearest neighbors to each point. What I want to do here is I want to add something, because currently all this sub does is it's going to create those lines, but it's not going to set up the attributes that we created on those points, like the anchor ID, the original point number, and we need those for our constraint network to work. So what I'm going to do is I will add some lines of code here, and first add 2 variables called pt1 and pt2 for the 2 points that are being connected with this current step. So let's create those. So this is the first point, and this is one of the close points that we are iterating through in our current iteration here in the for each loop. So this will be the opposing point. So let's set the point attributes on those points. So these were the point attributes for our first point, and let's just copy them and do the same for our second point. Like this. Then let's draw a line between those 2 points and set the primitive attributes, constraint name and constraint type of the line we just created. So what we're doing here is setting up the primitive type, so it should constrain the position, and the primitive type itself is a wire glue, so it glues wires together. So that should be it. Keeping our fingers crossed, no mistakes in the code thus far. Let's just save this, head up 1 level, have a look at the scene, highlight the .NET, keep our fingers crossed, and hit play again. Nope, not yet. Let me check. Okay, again, sloppy me in the connect adjacent pieces. On the one hand, I don't need this here anymore. This was from debugging the setup previously, and I just stupidly retyped it. So let's just get rid of that. And also down here, I set a point attrib, where I should have set a primitive attrib. Let's try again. Fingers crossed. Let's hit play. Nope, still not yet. The beauty of debugging. Okay, this is really embarrassing, and this is the last thing I think that's needed until this thing finally runs. But I made a mistake in the .NET here, because I did not change the name of this wire object. The reason why that is critical is because I point in my constraint geometry, I point to this object, and I called it wire. However, in my .NET, it's still called wire object, so let's just rename this like this, and now the simulation should run. Okay, let's check the real-time toggle here. And the only thing that is annoying me a bit is these wires are pretty coarse, and the reason why I left this wire resolution so low was because of simulation times. However, what I can do is, after that DOPNet, I can just drop down a smooth sub, which by the way got reworked in Houdini 16 and is now yielding less error-prone smoothing, especially with this wire setup here, so that's a nice thing. And also what I can do before that is just resample my wires so I have a bit more points. So let's just drop down a resample node in between there and just highlight the DOP, highlight the point display, zoom in a bit, and we can see here this is really coarse. Then I resample it to be twice the point density and then smooth this. Now it looks much smoother with not much added simulation time. Perfect. As you can see, I'm still struggling my way through DOPs and through the wire solver, and I had help with this setup by Manu. The idea to keep in mind is that all those solvers that they are in Houdini expect a certain set of attributes and parameters, and you can find the names and a description of those attributes and parameters in the help file that accompanies a given solver. That is where I got the names for all these attributes that I set up here and that are driving my constraint network. So I think there is no way around reading in the manual a bit. Also, there are quite good master classes on dynamics on those solvers, on wires, and maybe stuff for upcoming tutorials. There's also the possibility to simulate wires using the PBD solver, that is the sand and grain solver. As kind of a postscriptum to this setup, I would like to mention that I set up an attribute in here that we don't need actually, which stems from another setup that I used as a template for this one. And in here in the attrib create, the thing that you don't need is the original PT number, which I already grayed out here. And when you head down into the connect adjacent pieces and scroll down to our attributes in here, you don't need the original PT number for this setup to work. So only the anchor ID, constraint name, and constraint type, as well as the name of the wire object. So I hope you had fun with this, or at least it wasn't too painful. If you create any artwork using this technique, please just send us a link. We're always eager to see what you guys come up with. And it's cheers and goodbye.